Similar to finding the gradient at a point, like we did in a previous video, you may be required to find a point when you already know the gradient. And this uses a very similar process as we did in the finding a gradient at a point video. There's just a few minor changes that get made. One outcome we will notice is that in various functions, when we're finding out where the point is that has a certain gradient, we will find that there may be multiple points that have the same gradient. So this occurs when we have a polynomial of varying degrees of how many values of x essentially we can find that have the same gradient as each other. So what we're going to look at today is we'll take our first function here, which is a cubic. So we're going to x to the third power minus 3x squared minus 19x plus 10. And what we're going to do with this is we want to know, as part of this, where is the gradient value equal to 5? So the way we're going to go about this, well, we're talking about gradients here. So we initially need to make sure our function is looking at the gradient function. So to get to that, we're going to be using differentiation. Let's break down. dy over dx is 3x squared minus 6x minus 19. Okay, so we've done our first step. We've broken it down. We have our derived function. Now we need to incorporate the fact that we know the gradient is 5. So, because we already know the gradient is 5, we can just put that as equals. It equals 5. Okay. So, 3x squared minus 6x minus 19 is equal to 5. Okay. Now we can rearrange this so that it's equal to 0, and we do that by subtracting 5 from both sides. And we're going to get minus 19 minus 5, minus 24 now. And now we just have a quadratic that we can solve to find for x. So we can just go through that process. So, keeping it still at 0, I'm going to divide all by 3, just to keep it nice and tidy. It's 2. And then, sorry, that 2 is not very good. I'll redo that, and that x. There we go. And then we can just factorize that as it is. So it's going to end up being minus 2 and 8, so x plus 2, and x minus 4 will give us that. So it gives us a value of x equals negative 2 and x equals positive 4. So what this is telling us, excuse me, is that when this function here is at x equals negative 2, or when the x value is at 4, it will have a gradient of 5. And we did that by substituting in the 5 and then solving it or rearranging it to equal 0 and then solving it just as a quadratic. So you can carry on doing this with a number of, or any polynomial that you have. We have our x value. We could go ahead and then find our y values just by substituting in this x value into the initial function to solve what the y value is at those particular points. And we'll end up with 2 different points. And the reason we do end up with 2 different points is because we've got our quadratic like this. And we're going to have 2 situations where it's at positive 5. So one of our situations might be here, looking at along here, as being positive 5, so that's touching that point. And then the same one is going to exist over here, and we're going to have it being the same gradient at 2 different points. So we're going to have our x is negative 2 and our x equals 4 will be at those 2 points. So that's why we end up with 2 when we've got this cubic. If we only had a parabola, then we're only going to end up with one x value that has a gradient of 5. If we add an x to the power of 4, then we're going to end up with 3. areas where the gradient would be positive 5, because with this end here would start to curve around again and would create that third section that would have a gradient of 5. But in this example we didn't have that. We've just got it as a cubic, so it stays like that.